Welcome back. Now we're going to talk about graphs of functions in two variables, as well as, developing them based off considering the level curves as well as the contour curves. So considering this, we've got two ways or two methods to visualize functions in two variables, or rather z equaling some function f of xy. So one way is going to be to draw and label the curves for which the function has a constant value. So what that means is we're going to say, hey, let's let, y equal this value, or y equals 3, y equals 4, y equals 5, and see how that makes the function change. All right. Or the other way we could do this would be to sketch the surface in space. I don't like the way that looks. Sketch the surface in space. So we're going to get some examples into helping us think about the difference between these level curves and contour curves and how they can help us build a three-dimensional figure. So I do want to pull this definition from the book. So what we have here, the set of all points in a plane, z equaling some function f of xy, so this is a third variable z, has a constant value of f of xy equals c. So if we create this constant value, we can let that be a level curve. And the set of all points, x, y, and this constant value c in space is going to give us xy ordered pairs. So we'll be able to create a line or a curve or maybe a circle or a parabola. So looking at how all of those graphs change as this constant differs, this is going to help us develop this surface z being a function of f, or a function f of x and y. So let's do an example. Suppose I tell you that z is a function of x and y. Z being a function of x and y, that is a surface in 3 space. So my example here, we have f of xy equals the square root of 4 minus x squared minus y squared. And we want to create this graph in 3 space. All right, so the first thing we should do, f of xy, that just means our third variable z, so I'm going to replace that with z. So the function I'm dealing with is z equals the square root of 4 minus x squared minus y squared. And now this doesn't necessarily look like something we've seen before. This is kind of new to us. So one thing we're going to do is we're going to try to manipulate it and make this look like something familiar to what we're dealing with. So if I squared both sides, I have z squared equals 4 minus x squared minus y squared. And pretty easily I can see to move those x and y terms to the left side of the equation. I have x squared plus y squared plus z squared equals 4. So this represents a sphere of radius 2, the square root of 4. All right. Oops, I've got a square symbol missing there. X squared plus y squared plus z squared equals 4 is a sphere of radius 2. Now, is the domain going to be this entire sphere? So in the previous video, we talked about domain. And if I come over here and I go to think about the domain of this function, what I know is that that argument 4 minus x squared minus y squared, we know that has to be greater than or equal to 0. Or rather, negative x squared minus y squared is greater than or equal to negative 4. Dividing by that negative x squared plus y squared is less than or equal to positive 4. So we know that our x and y points have to be inside this circle of radius 2. But thinking about the fact that this is a square root, are my z values, my outputs, are those ever going to be negative? And the answer is no, because you're always going to get a positive output from a square root. So we also know that my z values have to be greater than or equal to 0. So I'm going to scroll down here, give myself some space. I'm going to think about graphing this in my 3 space. So this is a circle, a sphere at the center or on the axes. We have a circle of radius 2. So I'll go out 1, 2, 1, 2. And we know that circle would go up 2 as well. So if we were drawing a sphere, it would be a circle in all 3 of those axis planes. But because my z values have to be greater than or equal to 0, those outputs are always going to be greater than or equal, it's only going to be the top half of this sphere, or a hemisphere. And if I think about trying to draw that, let's see, I'll draw with my light crayon first. There's my circle, my base in that XY plane. So drawing that a little darker. We've got that coming out to the front. We've got this coming up here. Really should be a little more circular. And then this back piece, this is dotted because we can't see it. So it's a circle. It would also extend out in this direction and then back down here to that base as well. So essentially, I'm drawing a circle on all 3 sets of my axes. In my XY plane, it's a circle. So the base of this is a circle. If we look at what's occurring right here, this is in the ZY plane or the YZ plane, and it's only the top half of that circle. We're not drawing this bottom half here because Z has to be greater than or equal to 0. Same in my XZ plane, we would have a circle that runs through here, but in this case, it's only the top half of the circle. So we've created a hemisphere of radius 2. All right, so let's do another example. We're going to graph again in 3 space. In this situation, we have that Z is a function of xy, which is 1 minus x, no squared, 1 minus x minus 1/2 y. So looking at this, what is this going to be the graph of? And we should all recognize here that this is going to be a plane. We have nothing squared, we just have x's and y, right? So nothing squared it's a plane. And the easiest way to graph a plane is going to be to use those intercepts. So in order to find the intercepts, I'm going to let yz equal 0, xz equal 0, and xy equal 0. So my function z equals 1 minus x minus 1/2 y. So the first thing I'll do is I'll let y and z be 0. And if I were to do that, I have a 0 and a 0, 0 this, 0 that. Add that over. I'm going to get that x equals positive 1. So that's my x-intercept. For my y-intercept, I will let x and z be 0. 0 this, 0 that. Move this over, multiply by 2, I get y equals 2. And lastly, we will let x and y be 0, which is very easy for us to see. We get z equals 1. So I have 3 ordered pairs that are going to help me plot this plane. So I'm going to draw this. All right, 1, 2, 1, 2. So plotting some points, I have a point on the x-axis at positive 1, a point on the y-axis at positive 2, and a point on the z-axis at positive 1. So my graph here, now if I connect these, it gives me a triangular region. But these are just 3 points on this plane. This plane extends in all 3 of those, off of all 3 of those lines infinitely in all 3 directions. So we graphed a plane in 3 space. And just to reiterate, the plane is not shaped like a triangle, but we're using those intercepts to let us see where this plane, like if I were to lay a piece of paper down that was larger than that triangle, that would be the expansion of the plane. And of course, it expands out in all 3 or all of those directions infinitely. All right, let's look at one more graph. So for this example, we are going to graph z equals a function of xy is 100 minus x squared minus y squared. So we can get rid of that f of xy and just say z equals 100 minus x squared minus y squared. So what is this? We learned about quadric surfaces in chapter 12 prior to this. So what quadric surface is this going to represent? And I'll pause for a minute to let you guys think, but this is a paraboloid. So we want to recognize that that's a paraboloid. So in standard form, it would be more like x squared plus y squared equals 100 minus z, right? And you see we've got our 2 squared, so that makes it an elliptical paraboloid. Z is not squared. Okay, so let's think about this. The first thing we might do would be to try and plot the level curves. So the level curves are going to occur when I let z be a constant number. So to plot the level curves, we're going to let z equal some constant c. So let's plot, I'm going to plot 3 level curves. Let's plot z, I'm going to write it this way, z equals f of xy equals 0. So if I let z be 0, I'm going to get a circle of radius 10. How about if I were to plot z equals f of xy equals 51. So if I take this 51, I plug it in up here. 100 minus 51 gives me 49. So x squared plus y squared equals 49. That's a circle of radius 7. And our last one here that we might plot, z equals f of xy. I mean, we can do this infinitely, but I'm just choosing some numbers randomly that I know are going to work out. So if I take 75 and I plot that in here, 100 minus 75 gives me 25. X squared plus y squared equals 25. That is a circle of radius 5. All right, so that's kind of giving you an idea, these level curves, by letting z be a constant number. I'm creating these level curves. So I have these concentric circles, radius 10, radius 7, radius 5. And that was just found by plugging in different values for z. So all three of these z values, 0, 51, and 75, were chosen specifically so that when I subtract them from 100, I would get a perfect square number. But there are infinite correct z values you can choose. I could even go so far as to say, well, let's let z equal negative 21. So I'm letting it be a negative number. And if I take negative 21 and I plug this in here, 100 minus negative 21 is positive 121. The square root of that's 11. So this is a circle of radius 11. So let's think about what all of these level curves look like in 3 space. So if we went out to 10 on all of these axes, essentially we'd have this circle of radius 10, then a circle of radius 7, a circle of radius 5, and we also have this circle of radius 11. So all of these circles are going to occur at different levels of z. Z equaling 0, this red circle is on the xy plane axes. My 51 and 75 z's, if we were to pull these up into the air, the blue and the purple circle, and then the orange circle would actually go down below. All right, so all of these circles together are going to kind of help us visualize what's going on. We have a small circle up in the air, and as these circles go down, they're becoming smaller and smaller. What is the largest number that I could make z? So if I were to plot z equal to 100, take this 100, plug it in there, 100 minus 100, that's a circle of radius 0, or just a dot, right? So it is a dot, circle of radius 0, right here. So that's kind of representing that maximum value. Any other value larger than that, I'm going to start have negative radii for the circle, which isn't possible. So rather to try and help you, or to draw this by hand to help you visualize it, I've pulled in the picture from the book, and you see those first 3 level curves we looked at graphing. Okay, so the level curves are all on the base. They're saying, hey, it's a circular region becoming concentrically smaller all the way to that dot that would occur. And that dot is occurring right up here at our max at 100. Right? Letting z equal 100. Z equal 51 would be right about here in the middle. Z equal to 75, a little bit further up. Okay, so those curves, as they move up around the circle, we think about, like 75 being there and 51 being roughly here, those are creating these, what we call contour curves. So contour curves mean the same thing, but they are actually lifted or extrapolated up into space. So I'm going to pull in one more picture to kind of help connect the dots of what's going on here. So you see here's a contour curve in space. The contour curve is the same radius circle as the level curve on the base. It's just lifted up to z equals 75. So we're taking all of these circles and visualizing this elliptical paraboloid, which is opening down. And as I said, this doesn't just end here. It keeps going down forever because at z equals, negative 21, we would have this other circle that we talked about. So this is infinitely expanding paraboloid. It's shooting down infinitely forever. If we were to talk about the domain of this, the domain is the xy plane, because as this shoots down forever, this circle is becoming infinitely larger. So it's any xy point. And the range here, range are our z values. And so we have a maximum z value. So the range is the set of real numbers for which z equals this function of xy is less than or equal to 100. All right, so we've done 3 examples in this video. We graphed a hemisphere. We just kind of did that by thinking about it. We graphed a plane by finding the intercept. And then we graphed this elliptical paraboloid by thinking about level versus contour curves. And just to reiterate, the level curves, these guys right here, occur in the xy plane, okay? So all of the level curves are in the xy plane, existing for the domain of the function. And again, the domain is all of that, and so those curves, all these level curves, are just concentric circles becoming increasingly large in radius, whereas the contour curve is in space in a plane parallel to that xy plane, which intersects our 3-dimensional quadric surface here. Okay, so the contour curve is in space, the level curve is on that xy plane. So I hope that helps you understand how to graph some of these spaces in 3-dimension, these surfaces, I should say, in 3-dimension. As always, email me if you have any questions.